So next what we'll look at are how we make each of these functional groups: the acid chloride, the anhydride, the ester, and the amide. And each of these can be made, in a single reaction from a carboxylic acid. So in order to make an acid chloride, we start with a carboxylic acid, and a reagent that we actually just talked about in the last chapter, thionyl chloride. So thionyl chloride, you may recall, is a good electrophile, and the oxygen can add in its lone pair and attack the sulfur. From here, that oxygen on the sulfur adds its electrons back in and kicks out a chlorine. We've got a positively charged oxygen down here. It loses a hydrogen. And ultimately what this has happened because we want to make this oxygen into a good leaving group. We can now have chloride come in, attack the carbonyl. That shifts the electrons up onto oxygen. And then the carbonyl reforms, kicking out the oxygen group and giving us our acid chloride product. We also get some byproducts, sulfur dioxide, as well as the chlorine leaving group. But notice that general pattern that we set up right at the beginning of this section for how, the acyl substitution reaction always has two basic steps. We see those here. And remember what those steps were is that we start with a carbonyl with some sort of group that's going to go away. Our nucleophile adds in, we form a tetrahedral intermediate, and then we get our product where our nucleophile has replaced our leaving group. Well, these last couple steps that I've drawn in orange here, you can see that's exactly what's happening. The chloride here, that's our nucleophile. This O sulfur chlorine, that's our, we had it labeled as our Y group on the previous page. But what we're seeing here is the chlorine attacks the carbonyl. We shift the pi electrons up onto oxygen. That gives us right here, where we did have the carbonyl, that's our tetrahedral intermediate. In our second step, the carbonyl reforms by the oxygen adding in its lone pair, and it kicks out our leaving group, giving us our product. So these two steps, the two steps that we started this chapter with, we're going to see those in every single mechanism in this chapter. Sometimes we may have to do a little bit of work, as we did here, to set ourselves up for that point. But those two steps are going to be, shown in every reaction in this section. All right, so we've seen here how to make an acid chloride. What's the purpose of an acid chloride if we've already said they're not the most stable functional group around? Well, basically, they're used primarily in synthesis because they're very easy to turn into other functional groups. And immediately we're going to see our first example of that. And our first example of that is how we make anhydrides. So while there's a few different ways to make anhydrides, a lot of it depends on whether or not you want your two R groups to be the same. If you want your two R groups to be the same, then there's actually a really easy way to do this. You take whatever that carboxylic acid is, and you might need some heat, but you just get two of them to combine, they kick out water, and you get your anhydride. The difficulty comes in is what if you don't want the R groups to be the same? And if you just mix, two different carboxylic acids, such as here, acetic acid and butyric acid, you could end up with, multiple products. You could end up with two acetic acids combining, you could end up with two butyric acids combining, or you could get one acetic and one butyric. And that's really not that favorable to get a mixture of products like that you have no control over. So instead, the better way to make an anhydride is to use a carboxylic acid and combine that with an acid chloride. Now, how does this work mechanistically? Well, the acid chloride, unlike a lot of other functional groups, we don't need to do anything with it to make it reactive. It's such a good electrophile that even a bad nucleophile, such as a carboxylic acid, will readily attack. And so the lone pair on the OH group will attack the carbonyl, and we shift the pi electrons up onto oxygen. And so you can see just immediately there's our first of our two steps of a general acyl substitution reaction. So that's going to form our tetrahedral intermediate. Second step is that tetrahedral intermediate breaks down by reforming the carbonyl and kicking out the chlorine. And as you can see, the only thing that differentiates our product from an anhydride is the fact that we have an extra proton on that oxygen. So from here, all we need to do is lose a proton, and we get to our product. And unlike what we talked about on the previous page, this method will give you just one anhydride, and it'll be the one with the R groups that you want. There's no risk here of getting other products because you specifically defined one of them as the carboxylic acid. That one's going to be your nucleophile. And you specifically, by making the acid chloride, made the other one into your electrophile. All right, what about esters? So the easiest way to make esters from carboxylic acids is using a reaction known as the Fischer esterification. And the Fischer esterification is a reaction that's been around for well over 100 years, dating back to the 1800s, and is a way that we can take a carboxylic acid and an alcohol, and we combine them to form an ester and also kick out water. This reaction generally requires an acid catalyst, and in many cases we also need to heat it. Now, if you recall back to where I started in this chapter, remember that I said this group here could be O- or OH, and that depends on the reaction conditions. When we are dealing with more basic type conditions like we did for making the acid chloride and the anhydride, that's when we see O-. But under acidic conditions, our intermediate, our tetrahedral intermediate, will have the OH group instead. So how does this reaction start? Well, the problem here is that a carboxylic acid is not a terrific electrophile. In addition, an alcohol, not a great nucleophile. And so you might ask, why don't we use the anion of the alcohol as our nucleophile? Well, the problem with using that is anions of alcohols like that are also strong bases. And so if you mix that with a good acid like any carboxylic acid, instead of getting nucleophilic attack, you'll get essentially an irreversible proton transfer, because the pKa difference between the alcohol and the carboxylic acid is in most cases more than 10. And now we've made a carboxylate ion, and carboxylates with their negative charge are in most cases not electrophilic. So we can't actually do this reaction under basic conditions like that. So what do we need to do instead? Well, we need to use acidic conditions as we've drawn in. Now, under acidic conditions, how do we think this reaction starts? Again, even though we've never seen this reaction before, we should have an idea, based on what we learned in the last chapter, as to the first step of this mechanism. Because with our 1,2 additions and 1,4 additions to aldehydes and ketones, anything under acidic conditions, our first step was always protonation of the carbonyl. And if you recall, by protonating that carbonyl, we made it a better electrophile. And by making it a better electrophile, now something that's a worse nucleophile, like an alcohol, is more able to attack. From here, we get a proton transfer from what was the alcohol to one of our other oxygens. And then the other OH group can add its lone pair back in and kick out water. Now, upon losing water, we get to our product, the ester. So do we see our 2 steps of nucleophilic acyl substitution again? We should. We have the first step here. alcohol adding into the activated carbonyl to form a tetrahedral intermediate. And then we have our tetrahedral intermediate breaking back down to reform the carbonyl. Now, you might notice that when I drew this reaction out, I drew every single step in the reaction as an equilibrium. And it turns out for the Fischer esterification, the equilibrium is often pretty terrible, right around 1 or, slightly above 1. And so you don't get, good transfer to product. And so this is a good example of where now, in order to get product, you need to take advantage of Le Chatelier's principle and push the reaction forward. The most common way that we do that for this reaction is often, you use the alcohol not only as your nucleophile, but you use it as your solvent. By using it as your solvent, there ends up being a major abundance of the alcohol, one of your starting materials, and that pushes your equilibrium to the right. Now, where might we use a reaction like this? Well, one example that might be interesting is if we start with this aromatic compound that actually has carboxylic acids at both ends, we can react that with this alcohol, or this diol that has alcohols at both ends. And so what you should be able to start to see here is we can form an ester like that between this alcohol group and this carboxylic acid. But our alcohol, our diol, has another OH group left here. And you could use that to react with another molecule of the carboxylic acid. And now you've got a carboxylic acid left, which can react with another molecule of the diol. And this chain can just build up pretty much indefinitely and form a polymer. But this is a very specific type of polymer. This is a polymer of esters, or in other words, something you might be familiar with, a polyester, which of course we're probably familiar with as a synthetic fiber that we use to make clothing. And it turns out the name polyester literally comes from the fact that polyesters are polymers of esters. All right, our final functional group in terms of this group of 4 is how we make amides. And amides, it turns out, are the most complicated. They may also be one of the most important functional groups that we can make in this type of reaction, because it's the reaction of carboxylic acids with amines to form amides that's responsible for how proteins are put together. When we put a protein together, we take the carboxylic acid from one amino acid, and it reacts with the amine from the next amino acid. That forms a peptide or an amide bond, and that's how we string amino acids together to form a protein. What makes the synthesis of an amide complicated is we cannot use a good nucleophile. So if you just mix a carboxylic acid and an amine together, basically nothing happens. So typically we think of it from what we've learned so far, we've got two options. We can use basic conditions and deprotonate the amide. But we can't use that because if we use the anion of any amine, well, that's also a good base. And it'll just result in deprotonating the carboxylic acid to form a carboxylate salt. Carboxylates, as we've said, are not electrophilic. All right, so if we can't do that, our next guess might be let's use acidic conditions to protonate and activate the carbonyl. Turns out we can't do that either. Because if we use acid, then our amine nucleophile will get protonated. And when it's protonated, that means there's no lone pair left. And it's not going to be nucleophilic. So what do we do here instead? Well, we're going to introduce a new reagent. This is known as DCC, or dicyclohexyl carbodiimide. And it has the following structure. So it's a carbon in the middle, double bonded to two nitrogens, and then each of those nitrogens are bonded to a cyclohexane ring. Now, when I redraw this on the next page, we're going to abbreviate those cyclohexane rings as CY because they don't really participate in the mechanisms, in any way that we need to worry about. And so that way we can avoid having to redraw them every single time. So in this reaction, we start with one of the nitrogens on DCC, removing the acidic hydrogen from the carboxylic acid. Now, the carboxylate salt is not a good electrophile. It's also not a great nucleophile, but in certain situations, it can be a nucleophile. And here we have a good enough electrophile for it to react. That O- attacks the carbon, lone pair shifts up onto nitrogen. Giving us that intermediate. And with that intermediate, we've improved the electrophilicity of the carbonyl. Why? Because the lone pairs on this oxygen are going to now donate in both directions. Not quite as good as an anhydride because we've got nitrogen instead of oxygen, but still enough to increase the electrophilicity. And so our amine here can be primary or secondary. Now attacks our carbonyl. And here you can see the first step of our acyl substitution mechanism. Because in this step, we make our tetrahedral intermediate. All right, from here, we lose a proton on that nitrogen. Let's go to a new page to draw that. But this step here is just a proton removal. proton transfer. That proton transfers up to this nitrogen. And then we get the second step of our acyl substitution mechanism. Carbonyl reforms, kicking out our leaving group and giving us our product. And we get two products here. First being our amide product that we were trying to form. And then, in part, what drives the reaction forward is we get this byproduct, dicyclohexylurea. And most urea compounds like this, it turns out, are not soluble in the solvents that these reactions take place. So often the urea will just crash out of solution as a precipitate. And since it's no longer in solution, it's no longer part of the equilibrium. And by removing one of our products, we drive the entire reaction forward.